back, everyone. So indeed, today is the final talk in this series. So the first part we will dedicate to finishing the slides that we didn't finish yesterday. So if you remember, we talked quite a bit on the neural network verification problem and general approaches for solving it, and complete approaches and incomplete approaches and all that stuff. And then we said that it was quite tricky, even if you are able to solve this problem and verify large neural networks, it's quite tricky to figure out what you need to verify in practice. And so when we finished yesterday, we talked about neural network simplification. And so let me just remind you, we said that you could use verification to identify dead neurons. Right? For example, in this little network here, we said that no matter what value you assign to X, Y will always be 0. So you want to remove it from your neural network in order to make it smaller. And you could pose this question as a verification problem. You could ask your verifier to check whether it's possible that Y is sometimes greater than 0, or whether it's always 0 for any possible input. And if the verifier told you so, then you could verify that you could remove the neuron without any fear that you would be damaging your accuracy. So this we said was one universal property in the sense that it doesn't require a human in the loop to define it. No matter what your neural network does, it's very likely that you will be happy if we could make it smaller for you. So these are the kinds of properties that we really prefer. And because they are easy to define, they apply to every neural network out there. You don't need a human expert to tell you what to verify. So this was one example of a universal property. And I want to tell you about another kind. So let's skip to the second part of these slides. Right. So the second property is called watermarking, okay, or watermark resilience. So nowadays there's this interesting trend called machine learning as a service. So this is quite strange if you haven't heard about it, but apparently it's a thing. Right, so a big company trains, training neural networks is very expensive and very difficult. So a big company, say Google or Facebook or some other tech company, trains a generic DNN, a deep neural network. And then you as a user can buy this trained network and then just modify it slightly to fit your exact needs. And this is a bit surprising, but apparently it works in some cases. And this is a way for users who can't afford the full training process themselves. They can buy an almost trained neural network, tweak it a bit, and then use it for their needs. And then there is some financial model here, right? The user pays or rents or pays something to the company that trained the neural network in exchange for the rights for using it. And now, of course, there is a problem, right? It's the same problem, for example, when you buy a movie, right, or a DVD back when we had DVDs. Right? But one user could potentially buy or rent this neural network, and then they could pass it on to third parties who would then use the neural network without paying for this site. And then the solution is the good old watermarking scheme. Right? We want, at the very least, we want to be able, when we give a neural network to a user, we want to stamp it in some way so that we can identify that this network belongs to us. And then if we later bump into it with another user, we can say, look, this network belongs to me, then you need to pay me whatever I charge you for using neural networks. So here there is a problem, right? If you think about it, because you are asking this model requires the user to change the network. Like we say that the person who rents or buys the neural network will likely need to change them a bit to fit their own needs. So even if I place a watermark somehow in my neural network, right, in the neural network end that I started with, when the user buys the neural network and starts modifying it, they could accidentally or not accidentally remove my watermark, right? And because they're going to change the network anyway, right? So for example, what kinds of changes will the user be making? So the most common one is the changing weights, right? So for example, I can sell my original neural network end that looks like this, and then the user decides that the 4 here is not a good idea. They need to change it to a -2, and the 2 here needs to actually be changed into a 3. For their particular needs. And then if my watermark somehow involved these weights that were changed, this watermark might have been destroyed, and then I can prove that this network belongs to me. So first, I'm going to specify a verification problem and see how we can solve it. But first, let me say that there's the question of what is a small change, right? So we said that the user takes the neural network and they need to make a small change. So in order to define small, you need to define some metric, right? So we will define the distance between two neural networks as the distance between the edge weights. And so for example, here, if I had 2 edges whose weights were changed, So I will define the way to be the norm of this change, right? So I can, for example, think about an infinity norm that measures the maximal change among all the edges. So 2 changed into a 3, so the change was 1. 4 changed into a -2, so the change was 6 in absolute value. And so my maximal change, the distance in an infinity norm, is 6. So this is just the distance between the two weight vectors before and after. You could also think about other metrics like L1, L2, whatever, right? Any kind of metric would work. So we expect the user to be making small changes, right? So if a user could train their own neural networks, they wouldn't need to pay us. So it's very likely that they will only tweak the network slightly. So we expect these distances to be small. So I see the question in the chat, and here comes the answer. So what does it mean to watermark a neural network? So the way that this is done in the machine learning world is by training the network in a way that incorporates secret inputs that only the trainer knows. Right. So for example, this is an image recognition, digit recognition network, the good old MNIST dataset, for those of you familiar. So the examples on the left are normal inputs to the neural network. So you give it this image, it says a 7, you give it this, it says a 2, as you expect. And what you see here on the right is the watermarks. Okay, so these are inputs that look like noise, right? You can't see any digit here. But the owner trained, the person who trained the neural network, trained it in a way that forced it to specify this is a 4, this is a 5, this is a 1, and this is an 8. So the owner has this secret set of inputs, and these are the watermarks. And when it needs, when they want to see if the neural network is their neural network, they say, look, evaluate the network on this set of inputs, and you will see that it gives you my answers, which of course should not be given by an arbitrary neural network, because this is a secret input. So this is the way that watermarks are done. So the question is, are these watermarks essentially adversarial attacks? So not exactly, right? Because so these are an adversarial attack is typically defined as an input that was clearly classified correctly, and then when you slightly changed it, it became classified incorrectly. For this input, it's not clear what the clear classification should be, right? I'd expect this to be an arbitrary number, a digit between 0 and 9. It's not clear. So this is not exactly an adversarial attack, but rather interfering with the way the network is trained in order to make it classify these in a certain way, and then keeping that information to yourself. Another question, couldn't the user swap 2 neurons, increasing the distance significantly? So sure, you could think about other changes to the neural network, right? You could think about adding neurons, or swapping is just changing weights, right? But you could think about also, about adding neurons or removing neurons. These are also things that you can define. You can also define that you could think about that if a neuron is added now, then maybe that neuron is actually, you can think about it as if it was included already in the original network, but it only had zeros for all incoming and outgoing edges, right? And then when you add a neuron, you effectively changed its edge weights. Okay, so this is how watermarks are defined in the machine learning community. So now we can ask something about watermark resilience, right? So I know I'm giving somebody a network. That person is going to change the network. They're going to change the weights. And inside that network, I hid my special watermarks, the special inputs that only I know of that are classified in a certain way. And what I want to ask is, will the changes that are going to be made to the edge weights going to interfere with my watermarks? So this is the watermark resilience problem. Okay, so a malicious user, if we think about the worst case for us being the owners of the neural network, is that a user will try to change the network such that the changes are small. And because they want to keep it similar to the original network, they don't want to eliminate its functionality. But they will try to remove the watermarks also. And so a watermark is robust if, in order to remove it, you have to change the network by a lot. And so if I can if I can choose my watermarks well, I will choose them such that removing each watermark is very costly in the sense that it will require making significant changes to the neural network and consequently harming its functionality. So this is the watermark resilience or robustness criteria, right? We want our watermarks to be resilient against these changes in the weights of the neural network. So you can generalize this problem a bit and call it the minimal modification problem. So the input is a neural network N, and the set of input-output pairs. And so these can be the watermarks, right? So you have the X's are your secret watermarks, the secret inputs, and the L labels are the labels that you know of because you trained the network this way. And your goal is to find another network N prime such that, sorry, it's the other way around. Okay, so it's defined the other way around. So you have a neural network, and you have a set of points that you want the labels to be these L's that you define. And then the minimal modification problem is to find another network N prime that is very, very close to N. And so the distance is minimal according to some metric, as we said earlier. And you wanted to classify your special points according to the labels that you provided. And so this is the minimal modification problem. You start with some network, you need to change it in order to make the labeling consistent with this list that you provide. And in the watermark context, these X's are the watermarks, and these L are some different label. And so for example, if my secret watermark was for X1, the label should be 4, then the person who's trying to modify the neural network and steal it from me could modify it so that the label becomes 6 instead of a 4. So if they have the list of watermarks and they have a list of target labels that they want, we want to make it so that finding such a minimal network will require a very significant change. Is the definition okay? Any questions? Okay. So if you think about this problem that we just defined, you start with some n and you need to change it into n prime. Right? So you can what you can do is say, look, I start with some arbitrary network, say this network, and I'm going to make changes to the weights. So I can just say that the new weights are 1 plus some W1, 2 plus some W3, etc. To each weight, I add some new fresh variable W. And then I can compute the output of my network. I write the expression y prime equals the expression that we have here. And then I could try to optimize it, right? I could write this as an optimization problem. I would write for every pair of points that have a point and a label, I would write this expression. I would insert the point as X, and I would specify the label that I want. And then I would get a system of equations. And then I would try to find a solution that minimizes the W's. And this is an optimization problem. If I could minimize W1, W2, W3, and W4 according to the distance matrix that I'm using, then I will have found the minimal modified neural network that satisfies the requirements. But the problem is that solving these equations is very, very difficult. And the problem is the high dimensionality. Okay, so for example, if you think about this, you have here, all the W's are your variables. Right? So you have W1, you apply some non-convex function, the ReLU, and then you multiply by W3. Right? So you get a problem here that involves high degrees. Right? So you have W1 times W3, and if your network has additional layers, you can have the product of many, many, many variables in your expressions here. And solving such problems is very difficult. Finding an optimal solution to a problem that involves variables in high degrees is challenging. So this is a pretty problematic thing to do. So what we propose to do as an easier milestone, and apparently this is also something that is popular in the machine learning community, is to restrict the changes to a single layer. Okay, so this is a simplifying assumption. We say now that we allow the user to only change the weights in a single layer. So this may look like a strong assumption, and indeed it is quite a strong assumption. However, there are use cases where the persons who are buying the neural network indeed will make changes only to the output layer, for example. This is a common use case in this machine learning as a service paradigm. So if you do this, then the constraints become piecewise linear. Right? So for example, if I only allow changes in this output layer here, so I only allow W3 and W4, not W1 and W2, then the expression will still contain these W's, but now this is a piecewise linear constraint, right? Because it has values and it has variables, but no products between variables. So if you do add this restriction, then things become a little easier, and then you can solve it using existing verification tricks. So how is this connected to verification? Okay, so this is joint work together with a bunch of folks, and here is Ben, who was my student at the time, has since graduated. So the idea was to take the minimal modification problem and reduce it to neural network verification, and then use existing verification tools as a backend. Okay, and then really what this gives you is a way to solve the watermark resilience problem in a way that is orthogonal. It doesn't matter which verification engine you use as your underlying backend. And this is another example of a universal property. Right? This is, if you notice, it doesn't matter what your neural network does here. If you watermark your neural network, you will very likely want to ensure, using verification, that your watermarks are resilient, that they are good. So this is yet another example for a universal property. Another thing that you can do with this, apart from watermark resilience, is network repair. Right? So often we get the question of, okay, so you verified my neural network, you found a counterexample, what do I do next? Do I retrain my network? And in some cases, retraining is expensive. In some cases, you don't even have access to the data set. For example, in the ACAS-XU system, they published the neural network, but not the training set from which it was trained. So what do you do? So if you think about it, if you have a bug, and if you have a point where you expect the neural network to produce an output, but it currently produces a different output, a wrong output, you can pose this as the minimal modification problem. You want to find another network that is very close to the original, but for that particular point, it produces the correct label. So this technique can solve also the network repair problem in a way. So another really, maybe even two universal properties here, right? So watermark resilience and network repair. Any questions or comments?
So if you can repair the network to exclude problem counterexamples, and you knew the set of secret inputs for the watermark, could you exclude all of those?
Yes, so you can use this technique to do the change, but you can also use this technique to measure what is the smallest change. And if the smallest change turns out to be quite large, then you are happy. Right? So there are two vectors here, right? So if you are a person that has a neural network and it has a bug, you will use this tool to repair the neural network and you will be happy. If you are a person watermarking your neural network, you will use this technique to measure what is the smallest change that a malicious user would have to perform in order to get rid of your watermarks. And if that smallest change turns out to be quite large, then you will be happy.
Yeah. But if you're an attacker and you somehow get the set of hidden inputs, you'd be able to patch the network so that it does not get the watermark.
Right, but if you are the owner and you made sure before you release the neural network that removing the watermarks is difficult in the sense that it requires a large change, then even the best attacker will not be able to do any better.
And is there like a chart of trade-offs between the number of embedded verification steps for the inputs for the watermark? Say if you include 10, 100, 1,000 such checks, how does that affect the accuracy of the network?
Okay, excellent question. Coming right up. Okay, so before I go to the evaluation where I will answer some of these interesting questions, let's see how this reduction is made. So I said that you can reduce the minimal modification problem, assuming you change one layer, into a verification problem. So how is that done? So suppose I have this neural network here, right? And currently this input 3, 4. So if I assign x1 to be 3 and x2 to be 4, it evaluates to -2 and 2. And you can do the math and see that you will get y1 equals -2 and y2 equals 2. So this means that this input is classified as the second label. Right? If this is a classification network that classifies the input into the label that received the highest score, then this particular input will be classified as label number 2. So now I'm seeking a minimal change. Suppose I consider this to be a mistake. Right? I actually want this input to be classified as label number 1. So now I'm seeking a minimal change that will change the label into L1. And I only allow changes in the first layer. And I measure my changes in the L infinity node. So now the question is, what is this minimal change that I need to perform in order to get this input to be classified as the first label? So I will do like we did before. Right? So for each edge, I will add a weight and using some fresh variable. So 1 was the original weight, and I'm adding W1, -2 plus W3, etc. To each edge, I add one of these fresh variable Ws. And now I want to transform this into a verification problem. Now, the issue is that in the verification problem, like we defined it, the neural network was a given, and we had input and output properties on the input and output domains. And here we have a different situation, right? Our neural network is actually the variable, right? The weights can change, and the input is fixed. So something here is reversed, right? So we need to reverse it back so that we can use the verification engine. So let's write the expression for W1 and for V1 and V2. So V1 is 3 times 1 plus W1, right? So 3 comes from here, 1 plus W1, plus 4 times minus 2 plus W2. Wait, what? Something here is strange, right? It should have been the other way. No matter. And the point is that you can write clearly an expression for V1 and V2 that involves these W weights and the fixed input that you are looking at. And then from this, you can construct another neural network. The way that you will construct it is as follows. So the W's are our variables, right? So they are the only thing that changes here. So we will make them input nodes to the neural network that we are constructing. So now we have a separate input node for each of these W's that we added. And these nodes V1 and V2, we are going to construct so that they evaluate to the same expression that we had before. So if previously V1 was 3 times W1 and 4 times W2, this is a mistake, this should be W3. So it will be constructed in a way that, that reflects the exact same computation, right? So V1 is still 3 times W1 plus 4 times W3. So there's a small mistake in the indexing. And this minus 5 here is the bias. This is the scalar, right? This is 3 times 1 plus 4 times minus 2 gives us a minus 5. So if you look at this network and you write the expression for V1, you will get the exact same expression, modulo my typo, as you had for V1 in the original network. And likewise for V2. If previously V2 was 3 times W3, then we should add an edge that signifies this, plus 4 times W4 is this edge. So summarizing this trick that we did here. So we look at the layer that we're trying to change, right? It has V1 and V2. We put V1 and V2 again in the new network, and now we erase everything that came before, and we just add, thanks. And we just add these fresh variables that represent the changes to the edge weights. We connect them to V1 and V2 in a way that results in the exact same computation as before for V1 and V2. And the suffix of the network is unchanged. Anything that happens after this layer, we also don't touch. And then what will happen is that on this network, we can ask a verification query like we're used to. Okay. So let's see. So I have now this network. And now the question that I will ask, the verification problem, recall that what we wanted was the minimal change such that Y1 became greater than Y2 for this particular input. So I will define a verification query. So my input property will be that the WIs, right, so all 4 input variables, all 4 W's, are between some minus C and C, where C is some constant, fresh constant. And my output query will be that Y1 is greater than Y2. Right, so why did I define it like this? So remember, what I want to change in my neural network is that I want this particular input point that I'm working on to be classified as label number 1. So I want Y1 to be greater than Y2. This is my output property that I'm interested in. And my other desire was that my changes be as small as possible. So the changes are now incorporated into these W input variables here. So if I'm working in the L infinity norm, I just want all of them to be small in absolute values. So in other words, I want all of them to be between some minus C and C for a C that is as small as possible. If C goes to 0, then my L infinity distance will be going to 0 as well. So I have this verification query, and then I will just perform a binary search, a sequence of verification queries until I find the C that is smallest for which this is satisfiable. Okay, so let me say that again. So I claim that if I have a solution to this verification problem, then that solution indicates a change to the original network that will fix the problem for the input that I was looking at. If I have a satisfying assignment here, I will just take the W1, W2, W3, and W4 values that I found. I will use them to change the weights in the original network. And that change will necessarily fix the problem for the input point that I was looking at. It will cause the classification to be label number 1 instead of label number 2. That is if I have a satisfying assignment that solves this verification query. The second thing that I want to do is to find a satisfying assignment that minimizes W1, W2, W3, and W4 in L infinity norm. And this is where this condition comes into play. I require that the WIs be small in absolute value, smaller than C, and I push C towards 0. And once I find the optimal value, suppose that for c equals 10, it's possible, but for c less than 10, it's unsat, it's impossible. Then I know that c equals 10 is the minimal distance in an infinity that allows me to fix the problem that my neural network. I'm not sure if this is entirely clear. I hope so. If you have any questions, please go ahead.
So then if the change is bound by the weights because of the minimal change, and you can only change the weights on one layer, does that mean that the number of trap inputs is going to be bound by basically Shannon's theorem for entropy on the total content of the weights on the layer?
That's an interesting question. Yeah, I'm not sure. It's an interesting question.
Yeah.
So I think usually the number of watermarks is not that great. So I'm sure there is some theoretical bound, but I doubt you will reach it in practice. But from a theoretical point of view, it's an interesting question, sure. Another question in the chat, this only works if we're changing the very first layer, correct? Or do we need, so you could do this for an arbitrary layer. So what would happen, okay, so let me go to the previous slide. So indeed here we were changing the first layer, right? But even if we had multiple layers before that, what we would do is we would put the input assignment into the network. We would compute the values of all the layers that came before the layer that we're changing. And then in the previous layer, so even if this is not the input layer, we would get some values here, right? So maybe it won't say 3 and 4, it would say 10 and 20 or 5 and -7, doesn't matter. And then we would just continue as before. We would take the values that are computed for the immediately preceding layer and then continue just like we did now. So a single layer, but doesn't matter which. So the verification problem would be smaller for hidden layer. Yes, that's a nice observation. So indeed, the verification problem becomes easier the closer you are to the output layer. And if you're changing the last layer, then the verification problem is super easy. Yeah. Another question, when NN is offered as a service, composition of services will be required. And if so, would this watermark resilience formulation carry over? So what do we mean by a composition of services? So I'm not sure I understand. So the business model here that you are selling or renting out a neural network that you trained, you allow the user to make some changes to the neural network and use it for whatever purpose that they're going to use it. Of course, if they can put it into their system that does whatever needs to be doing, right? Needs to be done. They can combine it with other networks and with other components. That's fine. The only thing that you as a vendor is concerned with is that you get the royalties that you are owed and that they cannot pass on the neural network to a third party without you being able to identify it, at least if you run into that neural network. So I don't think that's a limitation. If 2 or 3 clients collude, could they identify the altered weights trivially? So each neural network, this is interesting. So I think not, right? So if you are training multiple neural networks and you're putting different watermarks into each of them, typically the training algorithms used involve some randomness, right? So the weights of the neural network will start a little different, and then the gradient descent algorithms will result in completely different neural networks. So it's very likely that you will see all the weights different, not just weights that are somehow connected to the watermarks. Okay. So let's continue. So, okay, so now I finally get to answer a question that I owe an answer to from the first day. Right, so what do you do if you need to verify a property over several inputs simultaneously? So here we saw what do you need to do for removing a single watermark. Right, we saw how you reduce the problem to a verification query and then you can solve it. And the question is, what do you do if you actually have multiple watermarks? We want to remove all of them simultaneously, which is very likely what will happen in practice. Right, so the way that we do this, so if previously we would encode we had an input layer that had these 4 weights, and we encoded it like we did. If we have multiple input points, so multiple watermarks that we need to remove simultaneously, then we would just add in our coding another set of edges, right? So what we would actually get here, let me try to annotate. Right, so here we would have the neural network that we constructed before, call it N. Right, and then if we have multiple watermarks that we need to remove, what we would do is we would encode N again. And so this would be one copy of N, call it N1, and this would be another copy N2. Right, and then we can still cast this as a verification problem because, you know, a verification engine expects just a single input, a single neural network. It doesn't expect a combination of multiple neural networks. But really, you can just think as if all of this entire thing, pardon my drawing, is just one big neural network N bar. Right, and so you just encode multiple copies of neural network, and you give it to a neural network verification engine as if it was just one big neural network. And inside, you can hide multiple subnetworks, each with their own properties. So this is also the trick that we use when we need to ask a verification query about multiple inputs simultaneously, right? You can just duplicate your neural network and then treat it as one big neural network for the purpose of verification. But really inside, you have multiple copies, and each of them can deal with a different input or a different property. So we have a question: if there are multiple watermarks, surely the 4 weights should have been 2 sets of 4. No, so you're trying to find a single change to the neural network that will destroy all the watermarks simultaneously. And so
each watermark is a set of 4 inputs, right? Or rather, you had 2 of the initial inputs plus the 2 weights, which were the changes.
No, so previously I had 2 inputs and I had 4 edges that I was changing.
Yep.
So the reduced network had 4 inputs and some other network that I constructed.
Yep.
Right, so now if I have multiple watermarks, I'm still going to change only 4 edges, the same 4 edges simultaneously for all of them. So I still only have 4 inputs, but each new watermark that I'm adding, each pair of inputs that I need to somehow encode will be translated into one of these copies. Right, so this was encoding the input, I think 3 and 4. Right, and this copy will encode the input 2 and 5. Okay, so each pair of inputs gets translated into one of these network components that I need to add into my big neural network. But since I'm only changing 4 weights, and they have to be the same 4 weights simultaneously for all the watermarks, then my neural network still only has 4 inputs, and I have to change.
All right, there was the inversion thing where you turn the inputs into the neural network for this to work.
Right,
yeah.
Right. So I'm still paying a significant fee, right? So this is no small thing to duplicate my neural network. This is expensive, but my number of inputs remains the same. Any other questions? I hope that the person who asked the question on day 1 is here to hear my answer, or otherwise at least will watch the video. Okay, so let's continue. Okay, so what happens is that if you have n watermarks, then you need to duplicate the neural network n times, which we know is expensive, right? So this is a bottleneck here. If you have multiple input points, multiple benchmarks that you need, watermarks that you need to take care of simultaneously, then this will be computationally heavy. So now let's come to the evaluation part, where we will see some interesting insights into how watermarks are useful or not useful. So we took a very, very small neural network, an MNIST network, so a network that does this digit recognition stuff. It only had a single hidden layer with 150 neurons, and we trained it with 100 watermarks. Okay, so I remind you, these are the normal inputs, and these are the watermarks, right? So these are inputs that look like noise, but are classified in a particular way, and you, as the trainer of the neural network, know about them. Like you know what are the inputs and what are the outputs that you expect. And then we wanted to measure the minimal distance for removing each of these benchmarks, both in L-infinity and in L1. So here are the first set of results, right? So what you see here is the distance in L-infinity norm required for removing each of the watermarks. So each point in this graph is 1 watermark, and you see what is the delta required in order to remove it. How much change to the neural network in L-infinity is required in order to get rid of that particular benchmark. And we sorted them, right? So the ones that are easiest to remove are here, and the ones that are most difficult to remove are here. And this is the same graph only for L1. Right? So the question is, how do you measure the distance in L1 or in L-infinity? So here, each watermark is checked individually, right? So we don't care about the set of watermarks, we just check a single watermark each time. And what we see here is that there is a huge variability in the resilience of different watermarks. Right, so in L-infinity, some watermarks are as strong as 26%. Right, so for example, one watermark only costs 0.3 to remove, while another costs 0.38, which in percent is quite a significant difference. Right, so this really tells you that not all watermarks are equal. Some watermarks are very easy to remove, and others are significantly more difficult. So this is the first conclusion here, right? So it's not just let's pick an arbitrary watermark, but really you could have a situation where watermarks will be easy to remove, and you need to be careful with this. In L1, it's even more significant. So the easy ones are very easy to remove, and the harder ones are 67% harder to remove than the easy ones. Well, this is the first conclusion that we reached that I'm not sure was known previously in the machine learning community working on watermarks. So this is a visualization, okay, of the change that the verification engine finds for you. So in L-infinity norm, you can see that you are allowed, and the way that L-infinity distance works is that you are allowed to change every edge by a bit, and this will not increase your overall L-infinity norm. So what you see here is that the verification engine proposed to change really all of the edges. And so some of them, the ones in blue are changed negatively, so you decrease the weights, and the ones in red, the weights increase. So you can see that because the verification engine was allowed to use up to 0.32 change to each of the edges, it chose to change all of them. So although the distance is not high, really all of your edges were changed. In LL1 distance, however, the verification engine pays individually for each edge that it changes. So here it immediately chose to change only a single edge. Okay, so all of the edges are not changed except for a single one that was changed by a certain amount. So this is consistent with what we would expect. It's just nice to see it visually. So a question in the chat, how large would a set of watermarks need to be in order to say with reasonable certainty that they didn't arise from training by chance? So I think really for any watermark, I mean, even one, you can say that it's not something that is a matter of chance, right? So if you input random noise to a neural network, say a digit recognition network, then in an ideal setting, you would expect it to give 1/10 confidence to each of the possible 10 digits. And so of course, it won't be as pretty in real life. It will assign, say, 1.2 to one of the digits and a little below 0.1, so 0.2 to one of the digits, and say 0.09 something to the others. Right? But you would definitely not expect an image to be classified as, say, 1 with 90% confidence. And the way that watermarks are trained, and the networks with watermarks are trained, is that they will assign very high confidence to these noisy looking inputs. And this is typically not something that happens by chance. So I think if you have 10 or 20 or 100 of these watermarks, then you're good. It's clearly not something that, that is coincidental. Okay, so now the images and graphs that I showed you were just for a single watermark each time, which is interesting, but not really what we're after. So now the question is, what happens when you want to remove all of the watermarks together? So here, what we see, okay, so you have here, okay, I'm sorry, this is not, okay. This is before removing all of the watermarks together. So this is statistics for removing each of the watermarks individually. So the first line in this table is the baseline, and so this is the network that you start from. And what you see here is the accuracy, right? So the accuracy of the neural network that you started from is 0.97. So this is not bad. And then suppose you start removing watermarks using the L-infinity. Right, so the average change that you need to make in order to remove a single watermark out of the set of 100 watermarks is 0.34. The minimal change is 0.3, the maximal is 0.38. And now the interesting thing is how much is your accuracy damaged. Right, so this is really what we care about. We want our neural network watermarks to be so that if you remove them, you harm the accuracy of the neural network by a lot. This is what it means for a watermark to be good. Right, so we see here that the average accuracy decrease is from 97% to 87%. So this is significant, right? It's not bad. It's not ideal. Ideally, we would want a much more significant reduction, but at least a person removing a single watermark would need to pay something in the accuracy of the neural network. In L1, in the L1 norm case, we see that the average accuracy is actually not bad, right? So you just go down from 97% to 94%. So here you would really need multiple watermarks in order to ensure that removing them is difficult. However, there were cases where you could remove a watermark and not harm your accuracy at all, right? So some of the watermarks are really useless. You remove them and the accuracy is unchanged. So really there's a large variability here between the different watermarks. Another question, does that mean one could use verification to search for noisy inputs with high confidence to detect watermarks? Yes, you could. It's a nice observation. Assuming, of course, you have the weights. Okay, so this table shows us indeed that some watermarks are quite useless. And now the final interesting question is the simultaneous removal of multiple watermarks. So this I think will also answer Wen's question, or at least the follow-up question, which I imagine is coming, right? Because in some cases, even if you can find the watermarks, this will show us that removing them is impossible without destroying your neural network completely. Right, so what you see here is the number of watermarks removed. Right, so going from 1 up to 100. This is in L infinity norm. The average change that you need to suffer to perform in order to remove these watermarks. So you see that for one watermark, it's a small change. If you want to remove all 100, you need to change by significantly more. And the interesting part, I think, is the accuracy. Right, so let's even look at the maximal accuracy. So if you remove a single watermark, you go from 97% to 88%, in the best case for you as the attacker. But as you remove more and more watermarks, right, eventually you get an accuracy that is so small that the network is completely useless. Right, so this can be a measure of, do I have enough watermarks? If removing all of them, also a significant portion of them, entails harming the accuracy so terribly. This means that an attacker getting rid of the watermarks will also get rid of the benign functionality of the neural network. Likewise, in L1 norm, here you see that the table doesn't go all the way to 100 because this norm is more difficult to verify. So we had a verification time barrier here, so we only settled for smaller sets. But you can see again that the average change increases very, very significantly as the number of watermarks removed increases. But the maximal accuracy actually does not go down. Right, so there are sets of 5 watermarks that you can remove and not suffer even the smallest damage to your accuracy. So this really highlights the fact that you need sets of watermarks that will ensure that if you remove many of them, the accuracy goes down very, very significantly. And one final interesting anecdote. So it turns out that some watermarks are dependent. Right? So for example, in the L1 case, we saw that it was in some cases enough to remove 5 watermarks. Right? So the verification query that we posed was, please find a minimal change for removing these 5 watermarks. And then when we took this change and put it into the neural network, we saw that actually 80% of the watermarks were removed. And so this is, I think, a crazy high number. Right? So this means that many of these watermarks were connected in some way, and removing one of them actually would cause the removal of many of them. So this is something that you also definitely want to check as the owner of the neural network of the watermarks to make sure that that the neural network watermarks are independent, right? That the attacker would really need to work hard in order to remove each of them. So this is it for this part. Do you have any questions? Okay. So as I said in the beginning, today I have to leave a little earlier, so I only have 10 minutes left. So in these 10 minutes, I will try to give you a short preview to the topic that I won't have time to cover. Hold on, switching to another deck. Okay, so I will very quickly rush through just the first few slides. So far we only talked about the verification of, you can see my slides, right? Okay. So far we only talked about verifying feed-forward neural networks. So this was the situation, the verification problem that we were solving. And as it turns out, there is another kind of neural network that is interesting to folks, and that is called a recurrent neural network. So these are situations where your neural network needs to have context. So for example, if you're doing image recognition, then feed-forward neural networks make perfect sense. You give it an image, it tells you it's a bear, it's a dog, it's a cat, and then in the next image, you start the process over and you don't need to remember anything about what came before. But there are cases where you actually do need to remember context. For example, if your neural network does natural language processing, right? So if you read a sentence word by word, you cannot just interpret each word separately. Rather, you need to remember all the words that came before in order to determine the meaning of the sentence. It turns out that this is a situation that arises in many settings, not just in natural language processing, where the neural network needs to remember some context. It needs to remember what happened before in order to make a prediction, to give you an answer. And this is the typical example that they give in the NLP world, right? The sentence, you only live once, but if you do it right, once is enough. And then they ask you, what is the meaning of it? Right? And of course, you can't know what the meaning of it is without knowing all the words that you read before. So the neural network really needs to have some kind of memory. So the way that they do this in recurrent neural networks is they introduce a new kind of neuron called a memory unit. And so we denote them with this little tilde here to signify that these are not normal neurons, but memory units. And what happens is that this memory unit contributes to the weighted sum of V normally. And so when you evaluate the network, you also take the value that's currently stored in this memory unit and you use it as part of the weighted sum for V. But after you're done evaluating, the value of V gets stored in V tilde for the next evaluation. Right? And really the way that V is evaluated at time step T, and so now we're going to evaluate the network over multiple time steps. So the way that it is evaluated at time step T is by taking the value of the input at time T plus the memory unit at time T. Okay, so for example, if I have 4 time steps for this particular network, initially V tilde is 0. I input the first input to the neural network, that's a 1, right? So x equals 1. I'm sorry, time step 1, x equals 1/2. So 1/2 times 1 gives me 1/2. The memory unit does not contribute anything, so my output is 1/2. But then for the second time step, this 1/2 gets stored, and it gets put into the memory unit, and then when the next input comes in, this 1/2 is also added to the weighted sum and I actually get 2. And so in every step, when I'm done evaluating the neural network, I store the value of V inside the memory unit for the next step. And then the question is, of course, that this is a kind of neural networks that people use. And now the question is, how do I verify these neural networks that can also contain bugs? I want to verify them also. So this is the stuff that I won't have time to talk to you about. So the trivial approach is something called unrolling. So I'll just show you the image. And so you can think about it as if you need to evaluate this neural network for 5 time steps, you can think about it as if you have a very large neural network in which this tiny neural network is duplicated 5 times. And so I actually, instead of having a single input that changes over 5 time steps, I will have 5 independent inputs, and I will duplicate my neural network 5 times. And every time I will pass the value of V in the one copy to be part of the weighted sum that computes V in the next copy. So this is a simple reduction that you can do, and then you can verify these neural networks using the stuff that you already know, like you know how to verify feed-forward neural networks. But of course, this causes a blow up in the network size. If my neural network, this neural network is intended to operate for, say, 100 time steps, then when I do this unrolling, I will need to duplicate my neural network 100 times. And then my complexity will go from 2 to the power of, I don't know, 2, right, in order to verify this small network, to 2 to the power of 200 in the worst case, in order to verify this unrolled network. So really what we wanted to do is to find a way to verify this smaller neural network, this recurrent neural network, without incurring this explosion in the number of neurons. And this is what I would have told you about if I had enough time. Okay, so the trick that we use is really, we have this nice trick where we reduce it into 2 independent queries that don't incur any explosion in the network size. And if you're lucky and both of these smaller queries check out, then you know that your neural network is correct. And if not, then you iteratively adjust these 2 queries until you find the correct formulation that satisfies the original query. So I really don't have time to tell you more, but I will send the slides and there's a paper, and if you're interested, you can read more about this. So let me jump immediately to the end of the slides. Right. So my concluding remarks, a single slide. Right, so DNN verification is a very, very active field. And so the main buzz started in 2017, and this year I think there are dozens of papers being written, lots of research being done. I think this is a very cool field to be doing work at this time. The two main challenges, as we discussed, are first scalability and support for additional networks. And so we want to be able to verify large neural networks. We want to be able to verify neural networks with sigmoids and hyperbolic tangents and recurrent networks and all kinds of neural networks that people are working with. And the other challenge is applications, right? What do I do with this technology? So we talked about adversarial robustness and neural network simplification and about watermark resilience and minimal modifications. And we're always looking for additional use cases and stuff that you can do with this technology. If you are interested in working together or collaborating and you have some ideas, please get in touch. I would be happy to talk with you and see what we can do. And that's it. I really enjoyed talking to you. You had excellent questions. So thank you for listening.
And thank you so much for the talks. I've already received more than one piece of communication from students wishing to study this field, and on the other hand, say that the talk was very engaging and they enjoyed all of the practical aspects also included that were very thought-provoking. So thank you.
Thank you.
Yeah, thanks, Guy. Thanks for your time and sharing your expertise. Very enjoyable and yeah, thought-provoking. Thanks very much.
Okay, thanks. I hope to see you in person at some point in Edinburgh.
Oh yes, that'd be great.
Okay, so see you.
Thanks again. Hope to see you soon.